Okay, so for those of you who didn't hear, yes, you still have a quiz today. It's one question, you don't have to do it, just open it, look at it. And the whole backstory which led into this whole thing is, all right, I know you're smart. I know you work hard. I don't want you to feel shortchanged. There's a whole associated document of quiz questions that could have been on it, or I was thinking about putting on it. So if you're like, I want to know those things, look at it. If you're like, the reason I took anatomy was because of the joy of learning and I thought the human body was fantastic and all of that has been sucked out of my soul, get a tiny bit of that back, go watch something interesting on YouTube about like, does spontaneous human combustion actually happen? I totally went down the rabbit hole the other day looking at legitimate sources like, is this a thing? And the general scientific consensus is like, yes, probably, but no, not really. Anyways, there's a whole thing. And, you don't have to do spontaneous combustion. But something that you're like, this is why I wanted to be in anatomy, okay? Concerns? I don't know why, I was legitimately worried I was gonna get a little bit of pushback of like, are you kidding us? But it doesn't sound like this is the case right now. I'm now actually seriously wondering if we should just keep trucking on with the respiratory system, or are we in the headspace to be okay here? You can watch a beatboxer, oh, I can't say the word. What am I trying to say? Yes, beatboxer. Sorry, thanks, I struggle with words sometimes. Their vocal folds, we're gonna watch that for a while because it's cool. Things I should remember or know about that I'm not? No? Okay, we're good, great. We're on to the respiratory system, right? Yeah. Lots of parts of it. Most of these people are, well, I'm not sure how familiar we are with all of these, but we're just gonna take them through, and we're not gonna hit the lungs today unless we just move through things really, really fast. Okay. But this is where we're at, right? The respiratory system, unlike, say, the digestive system goes, it's end to end, right? Mouth to anus, it's a whole, there's a tube through you. The respiratory system, that tube doesn't go all the way through, right? You've got openings in the mouth and nose, right? And then all the way through the lungs, all of that is technically exposed to outside. The diaphragm features here, but that's internal as well. This is where we're at. We're okay with this so far? Sorry, let me check my record. I don't know why I feel like I have to check every single time. But last time I messed something up, so that was a bad thing. The point of this, well, remind me, what's the point of this whole system? Yeah, that's exactly what it is. It's exchanging gas. Whereas blood is moving a whole bunch of stuff, right? It's moving oxygen, it's moving nutrients, it's moving heat, right? The respiratory system is exchanging gases, all right? That gas exchange is going to happen in the lungs. It's going to specifically happen in the alveoli of the lungs, which sounds like, oh, Italian food dish personally, but it's a small part. Doesn't it? A little bit? Yeah, okay. But that's going to happen here. The things between the lungs and everything else, the passageways are trying to purify the air a little bit. So you're not breathing in too much dust and smoke and random junk. It also is trying to humidify the air, which I realize isn't a huge problem in, say, Missouri. But if you've ever tried to breathe and it's really, really, really dry, you know how it hurts a little bit? Same thing, it's also trying to get the air coming in warm. Because if it's cold, it makes it slightly more challenging. But we're okay with this so far? Point of the system? Not to be dumb, but a little bit. I'm going to describe to you the nose. I know you know what the nose is, but we're just here, right? About here in your face should be easily noticeable. You're like, if you see this on the anatomy diagram, like, what is this structure? Like, I've got this one, right? It's the only part that's actually like externally visible, right? It's there. It's divided by a nasal septum. Do you guys want a completely random side note tangent? I want to share a random side note tangent. Have you ever been like lying on your side and you're breathing through your nose and then suddenly one nostril just isn't participating? You've had this happen? And then you like have to roll over? Has this happened to people? Okay, it's a thing. And your book does not talk about it, but it actually totally is a thing. What's going on? This will never show up on a test ever, I don't think. Like the MCAT doesn't care, but it's interesting. You might have heard of like erectile tissue in, say, the reproductive organs, right? Cool. You actually have erectile tissue in your nose, which what it is, sorry, did I squeeze people out? No, you're good. Okay. It'll fill with blood and it'll get bigger, right? It'll puff up. So inside your nose, you've got some erectile tissue that will fill with blood and like cut off one side of it sometimes. It's not actually known why this is a thing. The thought is to legitimately make you roll over while you're asleep. So you're lying there and then your nose is like, yeah, no, we've been on this side too long. Closes it off and then you feel like you have to roll over. It's a thing. It's not super important, but it's kind of mildly interesting. Yeah, sorry. Back to the respiratories. It's not helpful for anything, but if you're ever super interested, you can try like timing it. Okay, super bored. If you're ever like in solitary confinement and nothing else to do, you can be like, okay, how fast is my cycle? Alrighty, alright. Anything, just as a reminder, anything that's open to the outside in the body is going to be lined with a mucous membrane, right? So you've got mucous membranes up in your nose, you're going to have mucous membranes the whole way through the respiratory system. Fair enough? This is where we're at. So this is the external part of the nose, right? And then there's a lot going on inside. Help me out with what your nose does. So your nose gets air in. Anything else it does? Yeah! Fake, sorry, like too easy. My daughter currently has this book that's like the human body, but it pops up. And it's like, what does your nose do? Your nose is for smelling. It's like, anyways, she loves it. It's great. Yeah, the anatomy, it's good, but the anatomy is very, very toddler-based, right? Anyways. But yes, the nose is for smelling. Yay, the nose. Do you see how you've got bone up through here, right? That like up here, you have your skull, and there's a brain up here, right? Do you see how there's little tiny holes there? Not that there's sponge bone here, but that there's actually physical holes right here. You've got, is it labeled? I don't think it is. Huh, okay. On the top part, on the superior part, up inside your nose, you've got olfactory receptors. They're there in the mucosa, and the olfactory nerve is going to go up into the brain, just right through there. This is why, amongst other reasons, some say respiratory viruses, if they come in through the nose, can go for olfaction. It's like right there, and they can go for it. This is also why when people get like rear-ended in a car, if they do that thing with their head really, really fast, it'll sometimes shear those, and they'll sometimes lose their sense of smell. Do you see this? Yeah. Okay, so olfactory receptors, we'll worry about the sense of smell next semester, where we talk about sensation. But the rest of the stuff has a whole bunch of mucosa, and it's moistening the air. It's also helpfully trapping gunk. If you've ever, so, not to be gross, but like, if you've ever, say, been working in a really dusty factory, or been around smoke all day, and then you blow your nose, you can tell, you can be like, oh wow, gross, right? Other things that are happening, do you see, or inside the nasal cavity, there are those grooves. You see those? They're sticky out bits. Well, and sticky bits, they're covered. They're called conchae. They just increase the surface area, and it makes it so the inside of your nasal cavity isn't smooth. So air as it comes in has to like roll around and mix. It makes it turbulent. It's going to increase the time for air to get warm. It's going to increase the time for air to get moist. And it's also going to like mix air up inside a little bit. So the air has to hit the edges of your nose so you can trap more gunk. So far so good? So you've got your nostril here, right? Nose, stuff coming in. You'll see that the bottom part of the nose is also the top part of the mouth. You see that? That's called the palate. And there are two parts of it. You see how the anterior part, it's bone, and then as you get farther back, it's not bone. These are called the hard palate and the soft palate, or you can call it the anterior and posterior, with the anterior being hard and the posterior being soft. So far, so good? I've got, in your notes, I have a whole bunch of things that talk you through this, but we're going to stay on the picture here because I like pictures. Do you note, well, actually, I'm going to get a better picture here. Oh, sorry. Do you know the holes in the system? That you have like, yeah, you have bone, but there's a pocket. Those are called sinuses. The ones around the nose are called paranasal sinuses. Lots of holes around the nose. You've got sinuses in tons of bones, right? There's the one in your frontal bone, right here, right? You've got, there's a bunch. They're doing a number of different things. I've got a better picture. Here we go. That's the kind of, ignore the salivary gland. It's this whole system here, which looks a little bit creepy when you look at it, right? But you can see where they are, right? All your sinuses. And if you've ever had a sinus infection, you can totally see, they're like, yep, that's where they're at. I felt it. They're making it so your skull isn't quite so heavy, right? So it's not solid bone. That helps. They're also going to be making mucus that's going to drain into your nasal cavity. And they're also going to aid with speech, which you might have noticed if you've ever known someone who's, say, had a really bad head cold, and then they're hard to understand, right? But that's all we have to say about that. So far, so good? Next, we're going to move on to the throat. In anatomy, the throat is called the pharynx. It's right here. Well, okay, the pharynx is a little bit higher up than just what you probably think of with throat. It's this passageway between the nasal cavity all the way to the larynx, which we'll get to in a sec. It's this passageway right here. It's divided into nasopharynx, the part that's right behind the nasal cavity, oropharynx, right behind the mouth, and then laryngopharynx, which is the part that's attached to the larynx. Nasopharynx, you're just expecting air to go through, right? But, and this is important here, people, The oropharynx and the laryngopharynx, I have a hard time speaking sometimes, those, both air and food goes through those, right? Hopefully not at the same time, but both air and food are coming through those. This is how come you can choke, right? This is also how come you can speak. So, briefly, the positioning of the voice box where it is in humans is great, and it gives you a ton of control, and your ability to speak is phenomenal. The side effect of where it's sitting means choking's a thing. You probably never actually heard of, I don't know, like a cat or a dog choking. I mean, it can happen, but it's not, well, maybe you have. Okay, maybe you have, it's fine. Dogs eat everything. But it's not a big deal for most animals, right? There's not like an animal version of Heimlich that most people know. Humans have a harder time just because of how this is positioned, but usually we're fine. We're doing okay? Pharynx? Yeah. You also have, let's see, I look at pictures. You also have more called tonsils. You've got a bunch of them. I'm not sure how much we care about this. We'll come back to this depending if we have time, or we'll see it next semester. You've got tonsils a number of different places, right? You've got tonsils there by your tongue. You've got tonsils, the ones you actually probably think about when you, like your palatine tonsils, if you say ah and look down, that's what people are looking at. Typically right here. You also have these ones right back up here. Yeah, they play a role in infection and other things. For now, they just exist. The part where it actually gets interesting, is the larynx, the voice box. This is where it gets cool. I have 3 videos to show you, but we don't have to listen to all of them. Or videos you can look at. One video, it's this singing guy again. It's a singing voice box. I don't know that we should actually look at it, but it is beautiful and it's amazing. The one I actually think we should watch is this one in purple. Online folks, we're watching this one in purple here. Okay. Come on. Hello, would you mind closing the door? Thanks. I realized the friendly librarian behind there, she closed the door just when we were listening to Schoolhouse Rock the other day, and I realized it might be annoying if you're trying to focus. Oh, too loud. Oh my goodness. Is that loud enough? There's a lot of intro. The interesting part starts here.
ENT doctor and laryngeal surgeon, Matthew Broadhurst.
I would also like to point out, this guy probably has never been introduced that way before. Like, ta-da! Like, this guy's like, okay, I usually just, do my thing.
Thank you, Tom. Thank you. And a very good evening, everyone. It is a pleasure to be here on the TEDx stage tonight.
Yeah.
Whew.
Loud enough?
He's not warming up his hands. Doesn't get that intimate. We set out a little while ago to try to go deep into the world and the throat of this beatboxer extraordinaire to try to understand how such a vast array of sounds are humanly possible. So this will be a world first.
Oh yeah, this will be the world first, live on stage, nasopharyngo-laryngoscopic analysis of a beatboxer.
So when we make sound, we take use the vocal cords to take air from the lungs and then turn it into a vibrating air column in the throat. If you think of it like a trumpet, we've got the mouthpiece, that's the vocal folds, and then the horn section is the throat. If we took your head off, took a bit of your neck off, and left you as a torso with just your vocal folds vibrating, this is what you'd sound like. Pretty hard to communicate, but fortunately we've got a throat. We've got all the soft tissues, and that actually gives you all the incredible dynamics of sound that you'll hear tonight. Now this is a rigid laryngoscope.
Ooh, spicy boy.
I know. 10 millimeters in diameter, it gives us the highest resolution image of the larynx we can get. All right, you ready?
Can you imagine doing this on stage? Can you see it okay?
So that's the vibrating vocal folds, about 120 hertz. It means they've collided 120 times a second just to make that sound. And we can also see that they're absolutely perfectly normal. So all his beatboxing, all those sounds for years, with Tom's way of doing it, absolutely no damage whatsoever. That's really remarkable. Well done. Okay.
We got it.
All right. So watch now as the vocal cords go from high pitch to low pitch. You'll see them go from long and skinny to short and fat. And what you can see is that his vocal range is so extreme, much more extreme than any other performer I've worked with, the machine actually can't capture the really high pitches. So now we're going to swap over to the flexible laryngoscope. So hold on to the stomachs and let's see what we can do. So going to the back of the nose. And there you can see the soft palate. A lot of the sounds we make from day to day, even the simple ones, are incredibly complex. The sound k, for example, it's the soft palate sealing up precisely against the back of the nose. So if you say it loudly 5 times, feel your own soft palate snapping against the back of the throat. All right, so this is what it looks like when Tom does it.
Cut. A cacophony of cackling kookaburras and cockatoos and kakadoo couldn't quite quit ketamine.
All right, now in the beatboxing world, of course, they can use that for all sorts of different effects. Now we're going to slide down a little further.
Okay.
So what you can see there, that's the base of the tongue. The side walls of the screen, that's the pharynx, all muscle walls. And in the deep dark depths is the larynx. It's just his unique use of all the muscles and soft tissues, which lets him do all these amazing sounds that you're going to hear. So we will dissect some of these sounds for you now. So what he's doing is he's changing the shape and the length of the vibrating air column using rhythmic contractions of all the muscles to generate all those sounds that you hear. And now there's rhythmic movements of they're the arytenoid cartilages way down there, rocking back and forth to create that different sound. We like to call this sphincter bass. And what you can see is that collapsing all the tissue down allows a different kind of really deep bass note. All right, so with local anaesthetic on board, a big black hose in the nose, we're going to let loose a sliver of this repertoire and seal this in play.
To all my peeps who we came to get deep, deepest in your piss. Check this. We start from the basics and build from scratch. Yeah, like that.
Okay, it goes on for a while. We're all good? Alright. Let's see. Actually, that one's not that much more interesting. Okay, I'm going with white. Alright. Okay. We got our larynx. It's doing speech, it's doing other things too. The thing you really, well, you saw his throat doing all sorts of funky things? Yeah. Thoughts, concerns, actually? Can you imagine having a tubing on your throat and be like, be on stage, go for it? I don't know. It freaked me out. Okay, the larynx is, its main job in the keeping you alive department is acting as the gatekeeper, being like, okay, you know what? We want food to go down one side and air to go down the other side, and I'm going to make sure which one goes where. Fair enough? But it's also playing a huge role in speech. It's made up of a bunch of cartilage. Yeah, I'm gonna go through it. The thyroid cartilage, it's your Adam's apple. You can feel it if you mess around with your throat. It sticks out. The epiglottis is what's let me look at the picture here. Okay. I'm sorry, I stole this picture. Let's do this. There we go. That's better. I stole this picture, but I didn't put anything in. Okay, we're here looking at the larynx. You can see the epiglottis right here. Okay, you're seeing the thyroid cartilage, the sticky out bit. The epiglottis back up here. That's the part that's legitimately acting like the switch thing on trains, like route this way, route that way. It's gonna route food. It's gonna route food towards the esophagus, and it's gonna route air towards the trachea. All right. When you swallow, you should actually just try swallowing. The epiglottis comes up and puts a lid over the larynx. It goes up. So just to orient ourselves right here, you've got the esophagus right here, and the trachea right here. Remind me which one's doing food? Yes, absolutely. Are people okay with this? The esophagus is doing food, and the trachea is doing air. We're okay with those two? And you'll see the trachea is in front, the esophagus is back behind. And yeah, the epiglottis is going to go and cover the larynx, which is great because if the larynx, sorry, my mouse here, if the larynx is covered, you can swallow food and not have chunks of food end up in your larynx. You don't want that. That actually can be a big problem. Okay with that? Do you see right here these things, the vocal folds? That's what you saw in the video. They're the parts that are going to vibrate with expelled air. They're called true vocal cords. They've got this whole thing you can call the glottis. It's the vocal cords and the passageway between them. It's the glottis. And yeah, so we've got the vocal cords right here. You're going to be pushing air through that. It's going to be great. Moving on to the trachea proper. Yeah, right here. It's this nice little tube. It's about 4 inches long, so it's not huge. But you know, trachea. It's going to connect the larynx with the bronchi. So we'll get to the bronchi in a second. Walls are there. Okay. We've got the esophagus back here. We've got the trachea that we're looking at right here. It has cartilage that's shaped like this. C. It's shaped like a C, or half of a tube. It's going to keep the trachea open. And then when you're talking about like arteries that are kept open, or say the trachea is called windpipe, often kept open, people say that it's patent, meaning it's being held open. Which is good. This is not something that like opens and closes when you need to take a breath. It's just being held open in general. You don't want to get this crunched. We'll get crunched. This picture isn't perfect, but can you see the little hairy bits here? It's got mucosa that's ciliated, so it's got sticky out bits. And the cilia beat in the opposite direction of incoming air. So air comes in, and the cilia beat the opposite direction. And the idea is it's trying to get rid of, so as it's doing this, it's gonna be pushing mucus that's got debris in it. You're trying to keep particles of smoke, dust, pollen, other things out of the lungs. Okay? Oh, I've got a big picture. Kinda cool. Alright. Okay. So, now we've gone from the nose, right? Gone from the nose. We've gone through some sinuses, that's great. We've hit the pharynx, we've gone down the pharynx, we're following air in, right? Gone down the pharynx, gone past the larynx, through the trachea, now we're into the bronchi. The trachea is going to split. When it splits, it's now bronchi. Well, let's see what happens over here. Okay. You've got trachea right here, right? The larynx up here, you see where we are? It's going to split. It's going to split into both lungs, right? You'll notice, and maybe this weirds you out a little bit, the lungs aren't symmetrical. Like, they're similar. They're both similar. But no, this left lung only has 2 big lobes there you can see. Where you can see 3 on the right. And it's got this, like, notch out of it. Any ideas why the lungs aren't, like, symmetrical? Make room for the heart. Are we okay with that? You can see where the heart belongs. Yeah, they're not symmetrical. They're doing the same thing though. The right bronchi happens to be a little bit shorter and wider than the left one, just because how it comes in. But that's not a big deal. The bronchi is going to keep dividing and subdividing and subdividing into smaller and smaller branches. So through the trachea, it's one big tube. It's going to divide into two bronchi, and then those are going to subdivide and subdivide and subdivide. Great. Okay, we are going to get to the lungs, but we're not going to get much to the lungs. The lungs are taking up most of the space in your thoracic cavity. The heart, oh good grief. The heart is going to be here in the middle of the central portion, the mediastinum, right? But most of the rest of your thoracic cavity has got your lungs there. The lungs are divided by these grooves. They're called fissures. Left lung has 2 lobes. Right lung has 3 lobes. They're doing the same thing though. When you're looking at the lung, let's look at a picture of the lung. Yeah, here we go. Looking at the lungs here. The outside surface of the lung is covered with the serosa. It's covered with what's called pulmonary serosa. You've got a lung covering on the outside. You have. Sorry about the picture. Yeah. Okay. I did it again. I'm sorry. You have, when you're looking at the lungs, alright, you've got lungs here. You've got the heart, lung, you can see some folds in there. You'll note, just for record, you'll note there's a ton of blood vessels here, like a lot. This is going to become important. But, there's this outside covering of the lung, and then there's covering the lung that's like between it, right? So there's, it like touches the lung outside. There's what's called pleural, and pleural spelled P-L-E-U-R-A, not like more than one, but related to lungs. Anything that's pluribus, like pleurisy, it has to do with the lungs. Anyways, so there's what's called pleural fluid between the gap, which is going to be great, and you don't think about it until you think about what happens if it's not there. Your lungs are moving all the time, right? Changing shape. And the layers are going to kind of rub up against, or if there wasn't fluid there, they'd rub up against each other. Can we all take a moment to think about like friction, like if you've ever been like grabbing a rope over and over, you get it burns a little bit. Imagine every time you breathe, your lung rubs against something, rubs against connective tissue, or rubs against a membrane, or against something. Can we all feel like that's uncomfortable? Instead of doing that, you've got lubricating fluid between those two. So as it's going to move, it's going to decrease the friction between that breathing. So far, so good? Yeah. Great. Sorry, I love these words. I'm just gonna say, but I'm gonna show you here on these pictures. Okay, so we're going in. We've gone in through the bronchi, and things are just gonna increasingly branch. They're going to get increasingly smaller because they're going to branch and split, branch and split, branch and split. With the exception of the very, very, very tiny ones, they're all going to have cartilage in their walls holding them up. They don't collapse. Whereas like a lot of your blood vessels, if there's not blood in them, they flop down in on themselves. these air passageways in the lungs, with the exception of the very, very, very tiny ones, they're held. They're reinforced with cartilage. The naming convention is you've got primary bronchi, secondary bronchi, tertiary bronchi, bronchioles, the little tiny ones, and then the very, very little tiny ones are terminal bronchioli, which are going to have these little alveoli, little sac pockets at the very, very end. This stuff is where respiration actually happens, at least the part that we care about. You have lots of things going on. The little balloony looking things, you can call them air sacs. You can also call them alveoli, right? A whole wad of them, and we'll see how they connect in a second. That's called an alveolar sac. So one is a little air sac, or an alveoli. This whole blob is an alveolar sac. There are ducts, so there's going to be gas air that's going to be able to move through here, right? It's going to connect everything together. And then these little ones are the respiratory bronchioles. There's respiration's just taking place here. You'll see, okay, so we're looking here. We've got all these little, all my heaps. We've got alveolar sac right here. See that? If you go in and you're looking at it under a microscope, you'll see they're connected to each other, right? So you've got all these little alveoli. They're somewhat connected to each other with pores, and then they're going to open up into the duct. When you're looking at the microscope, you can see there is a massive amount of surface area, and it's super, super thin. So you see that? Like, really, really, really thin. We're going to come back to what this yellow stuff around the little air sacs does, what it is, but we're going to move on. But so far so good, we see this? These little alveoli, these little balloon pockets, they're not independent of each other. They're connected to their other buddies. When you've seen those like public service announcements on like smoking is bad for you, this is typically what you're seeing. Some version of something down here. Okay. So we've got our little air sacs, our alveoli. This is where we actually come into respiratory membranes. You've got a simple squamous epithelial layer there. Simple meaning what? Sorry, it's thin. Sometimes it's thin, but yeah, it's very, very thin. One layer sometimes is more, but typically it's about one. Squamous is going to be kind of flattened, right? They're, yeah, what else? All these things. Do I have a picture? Yeah, here's a better picture. Okay, you can see just like this one thick little epithelial cell here forming barrier. Pores connecting all these different air sacs with each other. You'll see blood vessels running through this whole thing. And so these are what's called pulmonary capillaries. These pulmonary capillaries covering all over this whole system of stuff. This makes an air-blood barrier, right? So on one side you have air, on the other side you have blood. And in good news, oxygen and carbon dioxide can exchange across this layer. This is why it's set up like this. And you'll see that wherever there's air, there's a lot of surface area next to blood right next to it. So you've got a lot of chance to switch things. So you're expecting. Well, let's look at these. Let's look at these little guys first. There are alveolar macrophages. Sometimes they're called dust cells, which makes me deeply happy. Because what they're doing is, when you breathe air in, you're also breathing other random gunk. Hopefully, hopefully the mucosal membranes and the cilia and all sorts of things have kept most big chunks out, right? You shouldn't like have an inhaled gnat down here, right? But you're still gonna get random junk. These little dust cells, these little macrophages, are going to pick up bacteria, they're gonna pick up particles, they're gonna pick up other chunks of junk. They're great. The little green cells in the picture, they're producing surfactant. You know how I should bring object lesson. You know how when you do the thing where you've got a glass of water and you're filling it up with water, right? And you can go beyond the rim of the glass. You can make it beat up. And like it's a cool thing to do in grade school, where you can put like pennies in, you see how high you can get it. Have you done this? People say this? Okay. Same if you haven't done this. Same if you like have a paper plate, and you see a drop of water on it, it beads up around, it doesn't go flat, right? Water has surface tension, right? It's cool, meaning water sticks to itself and it pulls, right? So instead of being just responding to gravity and being flat, it pulls up, punches up. This is great. Normally you don't worry about it, except like in the lungs, you want this this alveolar surface, it has to stay moist. Diffusion doesn't work well if it's dry. So it needs to stay moist, that's great. So there's water. The problem is water is sticky, especially when you look like microscopically, right? So water is sticky and it can end up like a sticky, making it so these little alveolar surfaces kind of stick together. They kind of like collapse into themselves. You've actually maybe seen this if you've ever, this is like weirdly specific, but I bet you've done it. If you've like blown up a balloon, deflated it, blown up a balloon, deflated it, you come back and it's like kind of moist because there's a lot of humidity in your breath. And you come back and the balloon's like all stuck to itself because the water's holding the sides together. You know what I mean? Alright, like it's deflated but it's stuck together. Water will kind of hold these little things together too. It'll collapse them in on themselves. So what you're going to do is you're going to squirt out a bunch of surfactant. It's basically this lipid molecule that coats the inside of these alveolar surfaces and makes it so it basically breaks the water tension. You can imagine pouring soap on water, it'll make it go flat, right? Speed it up, it'll make it go flat. It's the same deal. These little surfactant buddies, they don't come along in development until fairly late. And so when preemies are born, the big concern is often problems with respiration, and it has to do with this. They don't have the surfactant. So there are a couple ways to solve it now, but that's the scary part for that. But yeah, so far so good. The big point that's happening here is diffusion. This is totally on your lab. I feel like talking about it now, so go for it. Remind me how diffusion works. Just not in the human body, but just in general, diffusion. Concentration here, concentration there. High concentration, low concentration. Okay with this? Anybody have a problem? So far so good? Great. So if you have, say, a high concentration of oxygen, because you just breathed in a bunch of oxygen, you have a higher concentration there, and you have a lower concentration there in the blood. Fair enough? So blood is going to diffuse, oxygen is going to diffuse into the blood, in general. Not every single molecule of oxygen that's in the air in your lungs is going into the blood. Not even remotely, right? You can only actually get so much before it comes back the other way, right? So when you breathe out, there's still a ton of oxygen in your lungs. Sorry, a ton of oxygen in the air. So you're breathing air in, and air is not straight oxygen. People know this, right? It's like nitrogen and carbon dioxide and oxygen and a whole bunch of other stuff, right? But there's a lot of oxygen in it, that's great. But you're not even getting most of it out. So like if you do artificial respiration, right? Like someone's been drowning and you leap into heroic action and do the into their mouth, give them oxygen. You still give them oxygen. It's not like your lungs suck it all out. As far so good. Anyways, but it's going from high concentration to low concentration. Carbon dioxide is doing the opposite thing, right? There's fairly high concentration of carbon dioxide in the blood, because this is blood that's been through the whole body, dumped off a bunch of its oxygen, has picked up quite a bit of carbon dioxide. It's going to diffuse back out. So far, so good? Okay. Ooh, we have 5 more minutes before you need to leave to do your quiz, which won't take that long, but, it could take that long. This has gotten us through the, main structures. We're still missing the diaphragm, but the main structures of the respiratory system. Okay? But what happens when you actually breathe? What goes on? Yeah! Okay, this one I think people know, and it's probably maybe a little bit intuitive, maybe not. There are 4 big things that are going to happen. We're going to go through it, and I have every confidence that you're just following along just fine. The first thing is called pulmonary ventilation. Alright? Normal people call this breathing. Right? This is when you're moving air into or out of the lungs, right? You're ventilating your lungs. Pulmonary ventilation, you're breathing. Right? That's the first big thing. You're basically getting a wad of air and putting it in, getting a wad of air and putting it out. Right? Your body's going to do that just pretty much constantly, your whole life. This is good. Then you're going to have something that's called external respiration. This is happening inside of you, definitely inside of you, but it's where there's gas being switched off between the pulmonary blood and the alveoli. So this is when you load oxygen into blood and you unload carbon dioxide from blood. Alright? It's called external respiration because from the body's point of view, stuff inside these little alveolar sacs, it's still outside. Have we find that? Okay. So you've got pulmonary ventilation, moving bulk transport of air, external respiration. Then you're going to do bulk movement of gas, but this time it's through the blood. So you can have respiratory gas transport. So first you moved air, just as air into and out of your lungs. Then you had external respiration, switching gases between outside and inside. Now you have moving gases in a bunch, but this time in blood, so respiratory gas transport. And then the last thing is internal respiration. That's where down in your left pinky toe, there's going to be, or other places, not just that, all the places in your body. Gas exchange is going to happen between the blood and the tissue cells. Right? So just to make sure we're clear, and then I promise to let you go. When we're in the lungs, so oxygen's relatively high inside the alveoli, and carbon dioxide is relatively high in the bloodstream. Fair enough? Okay. If you loaded a bunch of oxygen onto this blood, and are now down in the foot, what's relatively high in the blood? Oxygen or carbon dioxide? Oxygen, are we okay with this? Which one's higher in the tissues? Carbon dioxide, are we okay with this? So, it's not like blood can only pick up oxygen. It's going to be able to pick it up, it's also going to be able to dump it. We're cool with that? Questions? Concerns? Okay, that's all we have for class. Did everybody get to see or acquire some random lab stuff? or you will at some point. Excellent.
I tried doing the model thing and it like flashed on its head.
I will bring a model. You know, no, okay. Too squishy? Did I get too cheap water bottles? Yes, I cringe.
Yeah, put the rubber band on the back of it and it just like
Crunch.
collapsed.
Okay, fine. I'll bring a model on Tuesday. So I actually hadn't tried it, but I'm like, this will be amazing. This is good. Yay for us. But no.